Welcome to another video lecture in Math 442. I am going to talk to you today about some things related to section 7.4. So we're looking at linear systems of equations now, and I'm going to start by showing you some notes that are my handwritten notes posted on D2L. So follow along if you have them. Let's get started. All right, section 7.4 is really all about systems of ODEs, and I motivated this a little bit on class the last time we were together. The general form of a linear homogeneous system of ODEs looks like what you see there, and we're going to call that star for now, where A is, well, it's a real matrix of size m by m. And U is an m by 1 vector. This holds in the complex numbers as well, but we're going to tend to think of them as real numbers for now. I want to take you back to section 5.1 a little bit. So go way back to what we were doing at the beginning of class. We talked about the system in star, and it always has a unique solution given by the following, as you see here in the box, where e to the at has a very specific interpretation. And now you're going to have to go back to section 5.1 to think about what that means. Remember, we're assuming here that this matrix A it's diagonalizable. That means we've got a list of eigenvalues and eigenvectors, and those eigenvectors form a linearly independent basis of Rm. And if you recall, our formulation where we diagonalize looked like this. So go back and check it out. So A was diagonalizable, and that meant that the R matrix had all of the eigenvectors as column vectors stuck in the columns V1 through Vm, where the eigenvalues, the corresponding eigenvalues, were in this matrix e to the lambda t, which was a diagonal matrix. Now, lambda 1, lambda 2 through lambda m are the corresponding eigenvalues that match with V1 through Vm. Go back and review that before you look too much further at this video, okay? Recall that if we were writing down the solution to this linear system of equations, the thing we were looking at right here, we formed it by looking at this matrix right here, these e to the lambda t's times my eigenvectors times this vector of unknowns c. And c is where our initial conditions came from or will be worked out with. Now, I want you to take a minute and recognize the fact that if I look at the matrix vector multiplication that you see there, it can be written in this form. This is really a linear combination of the columns of this matrix that you see right here, this matrix, and the coefficients are simply C1 matches with this column, and C2 matches with this column. Likewise, all the way through Cm is multiplying this column right here. Okay, and if you look down on the next page, you see this linear combination of the columns of that matrix right there. And every column of that matrix is of the form e to the lambda it times an eigenvector. So now, the m columns of that matrix have this particular form. And now the c's are constants. Each of the vi's is a vector of constants. So the terms that you see here, e to the lambda 1t, e to the lambda 2t, all the way through e to the lambda m times t, those terms determine the behavior of the solution as t goes to plus infinity or minus infinity, or even when t is ranging over some long time interval. So now the question is, what does this have to do with the class we're talking about here? Well, now we're talking about absolute stability. Now that we're in the situation where we've got a linear system of equations, our absolute stability for a linear system of ODEs looks like the following. How do we treat it? Well, we start by looking at a test problem. And now our test problem is U prime equals AU, where A is the matrix that you saw above, diagonalizable with this form, similar to a diagonal matrix, if you remember those words from your linear algebra class. So what did we do with absolute stability before? Well, we started with our test problem, and then we applied our method. And where are we going to start? We're going to start with our old friend Euler, because that's where we always start, to give us some idea of what we should be thinking about. And now from here, this is Euler's method applied to that linear test problem up there, right? So now we're in the case where f of tu is simply the matrix A times u. So this is indeed f of Tn un. Now, let's see what we can use all of this diagonalizability of the matrix A to tell us. If A is diagonalizable, we are now going to replace A that you see here with this R lambda, R inverse, like you see there. And now we're going to do the same kind of thing that we've been thinking about before. We are going to do a snazzy little variable transformation to rewrite this equation in a slightly different form. And what is our variable transformation? It's this right here. So start with this equation, which you see right here, multiply by R inverse. And now once you do that, the R inverse here can multiply by that R so that things are a little simpler. And what happens then is that I recognize an R inverse U, n plus 1, an R inverse UN, and then over here is another R inverse UN. So now I'm going to take my Vn and I'm going to substitute. So my brand new system, my brand new update looks like Vn plus 1 is Vn plus k times lambda Vn, where that matrix lambda is a matrix with diagonal elements only. It's a diagonal matrix with lambda 1 through lambda m on the diagonal. And so now let's think about what this system looks like. One note I'll make is that if you think about it in terms of a matrix norm, the norm of Vn plus 1 is less than or equal to, this is a matrix norm times this vector norm. If you just came out of Math 441, you'll know that that's a significant type of situation. All right. So now let's go back and think about this expression and that expression. What does that matrix look like? What does identity plus k lambda look like? Well, the identity plus k lambda, if you take a minute or two, write down all the details of it, it looks like a diagonal matrix with diagonal elements. And those diagonal elements have the form of 1 plus k times lambda I, where I goes from 1 to m. Vi prime is lambda I vi. What do I need for that? Well, I need that z equal to k lambda I is in the region of absolute stability for that, for Euler's method, for that expression. And I need that to be true for each one of these lambdas. That is for I going from 1 to m. So what does that mean? That means I go back and I look at Euler's method and I look at its absolute stability restriction, and it looks like that. And it looks like that for each of those lambdas, each of those lambda 1 through lambda n. And so now we can apply this same kind of idea to any of our linear multi-step methods, only we just have to go back and look at exactly what that what that inequality was, okay? So what you can think about here is go back and look at how we analyzed absolute stability region of any given linear multi-step method. And the requirement is that K lambda P is in the stability region of that corresponding method for each and every one of those lambda P's, where P goes anywhere from 1 to m. That is, K lambda P is in the stability region for all the eigenvalues of A. All right, that is the first installment of videos. And when we come back, I'll be looking at some of those slides and finish those up from section 7.4. Thanks for watching.